In this module, we'll be learning all about Statistical Process Control, also known as SPC. This is something that follows on perfectly from the Taguchi loss function and is a fundamental part of Six Sigma. So let's jump straight in.
Statistical Process Control, SPC, is an industry standard methodology for measuring and controlling quality. SPC monitors how a process changes over time and reveals whether a process is stable and capable. Finally, SPC allows you to identify and differentiate between common cause and special cause variation, something we will explore in a minute. Carrying on with a similar example from before, let's imagine you are measuring the diameter of a gear being milled on a milling machine. The target diameter of the gear is 50 mm, but as with all processes, there will be some level of variation. Each gear will not have a diameter of exactly 50 mm. Some will be slightly bigger and some will be slightly smaller. Let's imagine the customer is happy with a gear diameter of 50 mm plus minus 1, meaning as long as it's more than 49 and less than 51, it is termed a good product that the customer is happy to accept. Anything outside these limits would be classed as a defect and not accepted by the customer. Now, as Six Sigma is all about preventing defects and using data to reduce variation, instead of inspecting products before they reach the customer and weeding out the bad ones, we want to try and increase the capability and stability of our processes so we don't need to manually inspect each finished product. Remember, inspection is not value adding, it is a symptom of poor quality. Inspection uses resources, it leads to defects still slipping through the net and results in an extra cost that needs to be added to the price of the product or service. That is where SPC comes in. If you were to record the diameter of each gear, you would find that it forms something called a normal distribution, also known as a bell-shaped curve. This distribution will have a mean diameter and a variation. If you were to gather a large sample size, you would find that it fits this normal distribution shape. For this example, this process is both stable and capable, and we'll talk about this a bit later. But as you can see, its distribution lies within the lower and upper spec limits. These spec limits are decided by the customer, whereas the control limits are dictated by the process. Because the control limits are within the spec limits, we can say that the process is capable. Before we go on, I'll quickly explain the difference between stability and capability. Process stability refers to the predictability of the process to remain within its control limits. If the process distribution remains consistent over time, i.e. the output falls within the control limits, then the process is said to be stable. If the outputs are arranged outside the control limits, then the process is unstable. Process capability is a measure of the ability of the process to meet customer specifications, i.e. be within the spec limits. The process on the left is both stable, i.e. within the control limits, and capable, i.e. can fit within the spec limits. The process on the right is capable, as it could still fit within the spec limits. It is, however, unstable, as its distribution is moving out of the control limits. Remember, stability is the ability to remain within the control limits, not the spec limits. The process could be stable, but at the same time not capable. For example, this process on the left is stable, as it doesn't drift outside of the control limits. It is, however, not capable, as its distribution doesn't fit within the spec limits. This means that the process is stable, but stable in producing poor results. At all times, the process should be stable before it is capable. The process on the right is both stable and highly capable, as it's well within the spec and control limits. Now we know the difference between stability and capability, let's get back to the example. Now, if you were to transform that graph and instead have the diameter on the y-axis and time along the x-axis, you could plot the diameter of each gear as it appears. So what this is a control chart showing the process has recorded 8 diameters and all 8 are within the control limits of the process. This is an example of a process that contains random and what is known as common cause variation. This means the process is in control and experiencing natural common variation. We'll not go into detail too much about how these control limits have been calculated, but they are based on the outputs of the process over time, and they're calculated mathematically so that anything outside of them statistically shows that there could be a problem. When a process is in control like this, it is predictable, and we know the process is performing within its limits. Now if we look at another example of the process, this is out of control. This control chart shows something called special cause variation, and this signifies that the process is out of control. The reason it is called special cause variation is because it signifies there are abnormal or special conditions that have caused this. It could be that a bearing has worn and causing the drill bit to move. It could be that the drill bit is damaged or several other reasons. If data falls outside of the control limits like this, it indicates that an assignable cause is likely the source of the product variation, and something within the process should be changed to fix the issue before a defect occurs. Being able to identify these occasions of special cause variation are what makes control charts and SPC so powerful, as it provides a warning before a defective part has been produced. Remember, just because it is outside the limits doesn't mean it's defective. The customer specification limits are set independently from the process and control limits. So by identifying that a product has made it outside the control limits, a root cause analysis or investigation can be launched to regain control of the process before a defect is created. Tools like 5 whys and fishbone diagrams work very well here. The aim of Six Sigma and SPC is to embed quality and predictability into a process. We want consistent results. The greater consistency with reduced variation, the more capable a process is. With that in mind, control charts are used to detect patterns and signify special cause variation. For example, in this case, as the diameter has followed an increasing trend for 7 or more consecutive points, this means it is statistically significant and suggests special cause and not common cause variation. When a trend like this of 7 consecutive points or more in the same direction, again a root cause investigation should be launched to help determine the main causes so that they can be controlled. Perhaps there is an abnormal amount of heat coming from the machine, which is causing the drill bit to expand. Either way, the early detection allows the special cause to be investigated before a defect is created. SPC is all about providing these early signals that allow action to be taken before a defect is made. Every time special cause variation is identified and a root cause investigation launched, followed by an implementation of an improvement, the process becomes more and more capable with less variation. I must make a point here. The word apophenia describes the tendency to perceive meaningful connections between unrelated things. Caution needs to be made when looking at control charts. Humans are very good at spotting patterns, and sometimes need to resist the urge to do this. For example, if there are 6 consecutive increases in a row, an operator may see this and change the machine settings, with the prediction that the process will soon be out of control. By changing these settings, the operator has reacted to common cause variation and caused a change in machine conditions. This random common cause variation means the process is in control and doesn't need any adjustment or action. By changing the settings, this can cause the process to become out of control. For example, let's imagine the products were within the distribution shown. The mean diameter was 50 mm and the bell-shaped curve lies within the control limits. the process is capable. By the operator changing the machine settings, the distribution moves and causes the process to become out of control. As you can see, the area shaded in red would be below the lower control limits. So let's recap what we have learned. SPC is a great way to gain early detection of a process becoming out of control, so that action can be made before a defect occurs. That is the true power of SPC and control charts. It is a continuous improvement tool that allows process variation to be monitored and reduced throughout time. As special causes are identified and solutions put in place, the distribution of products should become tighter, as shown in the graph, and so should the control limits. Remember, the tighter the control limits, the less chance of a defect outside the spec level, and the more capable the process becomes. A final point to make is that this reduction in variation is not purely beneficial from a quality standpoint. As processes become more capable and with greater quality, you have the ability to charge more for your product or service. Let's imagine that you were originally producing shafts for the automotive industry with a tolerance of 50mm plus minus 1mm. If your processes become more and more capable, and you can start to offer customers shafts within a tolerance of 50mm plus minus 0.1mm, this increase in quality will result in an increase in sales, and also to customers that desire the highest of quality products. For example, Formula One companies that spend millions of pounds to save milliseconds on their lap times will happily pay a premium for the highest of quality shafts with the least variation.
So let's summarise what we've learned. Statistical process control is all about defining what is common cause and special cause variation. Common cause variation is natural within a process and signifies a process in control with a predictable outcome. Special cause variation signifies a process that is out of control and unpredictable. For that reason, you need to action it with a find and fix solution to make sure it doesn't happen again. Please be aware of something called apophenia, which is a human's tendency to spot patterns and act before they need to, so make sure you follow the rules. Finally, SPC is a continuous improvement tool, and it is used to continuously improve the process, reduce the variation, and make it more capable.